Greetings, everyone. Today we're moving on to Chapter 11, Equilibrium. Equilibrium isn't really a new concept that we're going to be learning. It's really a use of some previous concepts that we've already done. We're going to be taking special cases where the net torque on an object is zero and the net force on an object is zero. That's what equilibrium is. It's pretty straightforward. I think most of you will actually like it quite a bit. And this concept, equilibrium, is generally referred to as statics in engineering disciplines. So if you know that you have to take statics in the future, this is actually going to be pretty helpful if you understand the concepts behind it. For our first example problem, we've got the Hulk and we've got Thanos on a teeter-totter or a seesaw or whatever you called this thing. It's a balance where it pivots in the middle and you can put one person on each side and keep it steady. The Hulk is standing at the far left edge of the seesaw, and the Hulk has a mass of 525 kilograms. Thanos wants the seesaw to be perfectly balanced, as all things should be. Where should he stand on this if he has a mass of 750 kilograms to keep it perfectly balanced? I must say here that last time I taught this, I got a lot of hate over these numbers. Apparently these numbers are not canonical, so don't at me on this. Well, how do we figure this out? We want this to be perfectly balanced. That means that we want it to not be rotating. We want it to just remain steady like that and not tilt one way or the other. If it's tilting, then it's not perfectly balanced. To make it tilt, we would need to give it a torque. So now we see we don't want to give it any torque. We want the net torque on the seesaw to be zero. This is the beginning of equilibrium problems. Every equilibrium problem we do is going to end up having net torque is equal to zero. Net torque is equal to zero just because we don't want it to tilt. Well, what is the net torque on this? The net torque should be the torque from the Hulk wanting to pull it this way and the torque from Thanos wanting to pull it this way. Okay, well, which ones of those are positive and which ones are negative? Who is giving this a positive torque and who is giving it a negative torque? If the net torque is zero, then one has to be positive and the other one has to be negative in order to get that zero. They have to cancel out. So can you tell me who has the positive torque and who has the negative torque? Well, we figure out torque by drawing our line from the center of rotation right there, going out to where the force is being applied. So if we look for the torque from the Hulk, then we go out to where the Hulk is, where the force is applied, and then we look at the direction of that force. There is the direction of the force from the Hulk, and there is the direction from the center of rotation out to that force. We can see that the angle will be 90, which is nice, but to find the direction of it, we take our fingers along the first path and then bend our fingers to the direction of the second path and extend our thumb outward. The Hulk is going to apply a positive out of the page torque. You can also think of that as, well, the Hulk is going to want to spin it kind of this way, like this. The Hulk will be spinning it like this, and if I make my fingers go like that, my thumb goes out of the page. Therefore, that is a positive torque. When you want to draw that something is going out of the page, the symbol that you can use is a circle with a dot in the middle. That is an out of the page symbol. So this is going to be for the torque of the Hulk. On the other hand, Thanos, on the other side, you take your fingers, you go to where Thanos is, and then you put your fingers in the direction that the force Thanos is applying is going, and my thumb is going into the page now. It's going to be an into the page torque. You can also think of it as, well, Thanos is going to make the whole thing go this way, and my thumb goes down when I make that. An into the page direction is shown with a circle with an X. So this is torque Thanos. Why do we have these symbols? Well, it actually comes from an arrow. It's literally trying to look like an arrow. If you had an arrow, a modern arrow, and you pointed it directly at yourself, it would look like a circle with a dot in the middle, just like this pen, a circle with a dot in the middle, just like that symbol. On the other hand, if the arrow is going away from you, then, well, I don't have feathers on the end of this pen, but you would see the feathers kind of sideways, or from the back side on the end of the arrow. So that's the meaning of those two signs. The arrow going right for you and the arrow going directly away from you, and you see the feathers on the end. Well, we've determined directions. We're going to define out of the page to be positive and into the page to be negative. Then we can say, well, the net torque is just going to be the torque from the Hulk plus the torque from Thanos, or more particularly, minus the torque from Thanos. Torque Hulk minus torque Thanos, I can't spell, but you can't read my handwriting anyway, so it doesn't even matter, is equal to 0. The torque applied by the Hulk will end up equaling the torque applied by Thanos. And then we can replace that with the equations for torque. So the equation for torque, R cross F equals R cross F, but this is the radius where Hulk is, and the force of the Hulk, and the radius for Thanos is, and the force from Thanos. As I showed you before, the angles on both of these are actually going to be 90 degrees. So when we skip ahead to RH, FH, sine theta, as we always do, whenever we have a cross product, we're going to end up replacing it with just sine of theta. In this class, at least. In your math classes, your professors would yell at me for saying that, but I don't care. RT, FT, sine theta, and I guess this is the theta for the Hulk and theta for Thanos. Well, that's 90 degrees. That's 90 degrees. They both end up giving us 1. So we've got the radius of the Hulk, the force of Hulk, equals the radius of Thanos times the force of Thanos. The radius of the Hulk, what is the radius of the Hulk? Well, the Hulk, do I measure the radius of how fat the Hulk is? Probably not. That is the distance. That radius, what is that radius? Yeah, that's the distance that the Hulk is from the center of rotation. And what is that distance? That's 2 meters, half of the total length. Well, we've got 2 meters times the force of the Hulk. What is the force of the Hulk in this case? That's just going to be the force of gravity from the Hulk. The Hulk has gravity pulling down. And what is the force of gravity? It's not 9.8. It's mg, the mass of the thing times the acceleration due to gravity. So the mass, 525, times 9.8, that part is still true. That's equal to some unknown distance, the radius of Thanos, some unknown distance to the center of rotation, times the force of Thanos. Well, radius unknown times force, 750 times 9.8. Well, our 9.8s cancel. That's nice. Now we need to figure out what that distance is. We can do that fairly easily. We just need to take 2 times 525 divided by 750. And that gets us a decimal. D is equal to 1.4. What are the units on that? Meters. Now, does this make sense? We've got the Hulk and Thanos on this 4-meter long seesaw. The Hulk is 2 meters from the center, and he has well, that's a very large mass, but it's smaller than Thanos' mass. And so does it make sense that if the Hulk is 2 meters away, then Thanos would be 1.4 meters away from the center to keep this perfectly balanced as all things should be? Yeah, I think that that does make sense. 1.4 meters away. Great. The next question is, what is the force of the pivot point on this entire contraption? How much force is the pivot exerting to keep the whole, everything stable and going on? How are we going to figure that out? How are we going to figure out the force of the pivot holding everything up? Yeah, if it's holding everything up and holding everything steady, then the net force has to be 0. Okay, well, the net force is going to be the force from the Hulk pulling down, the force from Thanos pulling down, and the force of the pivot pushing up. What kind of force is the pivot pushing up with? Yeah, normal force. Okay, so how do we do this professionally? Well, we should probably just redraw it very quickly. We've got, I'm just going to draw boxes. We've got the Hulk pulling down, Thanos pulling down, and the pivot pulling up, pushing up. So how do we convert this into a net force equation? Yeah, we take all of our positives minus all of our negatives. Force Hulk, force Thanos is equal to 0. Normal force is going to end up just equaling force of the Hulk plus the force of Thanos. So the normal force is equal to the mass of the Hulk times the acceleration due to gravity, so 525 times 9.8 plus 750 times 9.8. And we can use our calculator to solve. 525 times 9.8 plus 750 times 9.8. That gets us 12,495. I'm just going to say that the normal force is 12,500 newtons. That's the force required to keep both of these guys from just falling through everything. When we did this and found how far away Thanos needs to stand in order to keep everything perfectly balanced, there's something that I did that I didn't even mention to you, and many of you probably didn't even notice. And that's okay, because what I did was pretty self-explanatory. I chose this radius here and here to be based on the distance to the pivot point. The distance to the pivot point. There's the pivot point. How far each person is from that pivot point. Well, the way that we define a pivot point is the point around which everything is pivoting. Pivoting is, going back and forth, up and down like that. So this would be the pivot point in this case. This here is the pivot point because it's pivoting right there. Technically, there is no pivot point here because nothing is pivoting. Nothing is actually moving. Can you actually say that it pivots around that point when nothing is actually pivoting? This is almost a philosophical question, but it actually makes things slightly easier for us because we don't have to choose all distances from that point. We don't have to measure all distances from that point. I've got another example. We still need to figure out where Thanos is going to stand. We already know that it's going to be 1.4 meters from the center of rotation, but we're going to calculate it in an entirely different way. Instead of measuring the distance from this point, we're going to measure the distances all from here. The far left end of the plank, the far left end of the seesaw. Well, no matter where we look, the torque around that point has to be 0. The torque around this point obviously has to be 0, because if it's not, then it will start moving like that. If the torque is not 0 around this point, then it will start moving like this, which we still don't want. That's also kind of impossible, but we also don't want it because we want everything to be perfectly balanced. If we're measuring from this point, then we don't want it to be rotating like that, and we don't want it to be rotating like this. We don't want it to be rotating at all. We can pick any point along this entire thing and say the torque is equal to 0 here. The net 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 torque is equal to 0 everywhere. Let's prove that by looking at the net torque on the far left end of the plank. I'm kind of saying that the hulk is actually standing right at the very last atom of this plank, and so this is going to be very, very slightly off the way that I've drawn it. But just imagine the hulk standing like a ballerina at the very edge, the last atom of this plank. Well, the torque at that point is 0. Now, what is applying a torque to this plank when viewed from this point? Is the hulk applying any torque? Remember, the equation for torque is r cross f. If we're measuring all distances from the end of the plank, what is the radius that we would plug in for the hulk? It's 0. He's right there at the end of the plank. Will the hulk apply any torque in this case if we're measuring from here? No, he will not make any torque in this. Thanos will. Thanos is going to be wanting to bend it this way. So that's, if you can see how my hand is going, that's down. So it's going to be another negative torque. So I'm going to write down that the torque from Thanos is negative. Is there anything else that could be applying a torque when viewed from this point? Yes, there is. This, the pivot point, can be said to be applying a torque to the whole plank when viewed from this point. Now earlier, we were viewing everything from this point. We were measuring all distances from this point. And so any force applied to this point would have a 0 radius and can be very safely ignored. But now that we're measuring things from over here, we can safely ignore the hulk, but we can no longer ignore the force from that pivot point. And which direction is that? Well, if we are holding this steady, then, and saying that nothing's rotating around that point, which it isn't, and we see what the rotation would be from this normal force, well, that's going to be like this, bending it up like that, and that's an out-of-the-page force, which is exactly what we would want, because if we just have a negative torque, then we're not going to be able to cancel out with anything to get a 0. So we have to have a positive torque from the pivot here equals 0. Therefore, the torque from the pivot is equal to the torque from Thanos. R cross F pivot is equal to R Thanos cross force Thanos. The sines of theta will end up being 1 again for the exact same reason as before. So we've got the radius pivot, force pivot is equal to radius Thanos, force Thanos. Radius pivot. Well, if we're measuring from there, what is the radius to the pivot? Yeah, it's 2 meters. 2 meters times the force of the pivot. The force of the pivot was this normal force that we got before, 12,500 newtons. That is equal to the radius of Thanos, which is the thing that we're going to look for again. We know what it's going to be. We know that it's going to be 1.4 meters. We just want to confirm that it's going to be 1.4 meters. Times the force of Thanos, well, that is 750 times 9.8. And I can solve for that pretty quickly. I can take 2 times 12,500, but I'm just going to get it from my calculator, divided by 750 times 9.8. And that's 3.4 meters. Is this right? 3.4 meters? Wait a second. I got 1.4 meters over here. How are we going to make sure that, that we're actually right? Well, here, on this one, I was measuring from the pivot point. Thanos was 1.4 meters from the pivot point. But on this one, I was measuring from all the way over here. And he is, in fact, 3.4 meters from all the way over there, from the Hulk. So this does actually make sense. And that's good, because this is physics. This leads us to a new concept called the center of mass. These equations give us the center of mass. They look only slightly intimidating, but they're actually far less intimidating than one might otherwise expect. The center of mass of an object in the x direction is going to equal the sum of all the masses that make up the big object times all their distances measured in the x direction. Take each mass, if you have something with a whole bunch of masses put together, and you want to find the center of mass, take the mass of each individual object and multiply it by its x coordinate, and then add all those together, and then divide all that by the sum of all the masses put together, the mass of the whole object. You do the exact same thing to find the center of mass in the y direction, and the same thing in the z direction, replacing x with y with z. Can we use that on this problem to find anything? Well, yes, we can. Let's use this to find the center of mass of the whole system. We've got the seesaw, we've got the Hulk, we've got Thanos. The Hulk is 2 meters away from the center. Thanos is 1.4 meters from the center. The Hulk has a mass of 525 kilograms. Thanos has a mass of 750 kilograms. Let's figure out where the center of mass of this is going to be. Actually, can you tell me where the center of mass is going to be just based on what you know about reality? Okay, let's see if you're right. X, center of mass. Are we going to be able to do anything with y or z? Not really. Everything is happening in the x direction. So the x center of mass is going to be the sum over all the objects of the mass of each object times the x position of each object over the sum of the masses. Okay, well, then we need to do this how many times? 2 times. We've got 2 masses. So we've got the mass of the Hulk times the x position of the Hulk plus the mass of Thanos times the x position of Thanos, all divided by the mass of the Hulk plus the mass of Thanos. Well, we can actually just go ahead and plug in numbers. The mass of the Hulk, 525 kilograms, times the position of the Hulk. Well, we have to decide where to measure this from. So I'm going to say we just measure it from there, from the end again. So the distance for the Hulk is going to be 0, because the Hulk is at the end of the seesaw. So times 0, because he's 0 meters away, plus the mass of Thanos, 750, times distance, well, from there all the way to there is 3.4 meters, as we discussed, and this is divided by 525 plus 750. Let's see what we get. 525 times 0 is 0. So we've got 750 times 3.4 divided by 525 plus 750. What do we get? We get 2. Does that make sense? 2? What are the units of that? Yeah, it should be meters. Well, the center of mass of this object is right there, right over the pivot point. Is that a sensible answer? Is that a sensible thought here? Yeah, if you want something to be balanced, you should probably support it at the center of mass of that object, unlike what I'm doing here. Oh, there we go. Yep, I'm supporting it at the center of mass, therefore it is remaining balanced. That's one way that you can find where to balance something, and you can find that using the center of mass. You can find that using torque around the center. You can use that, or you can find that by using the torque around one end. There's a bunch of different ways of solving this kind of problem, especially now that we know so much about physics. Thank you for tuning in to another relaxing episode of Art with Dr. Harris. I've got this next problem about holding a bowling ball with my fantastic art right here. This is actually supposed to be your forearm, or your arm, and I guess it's an x-ray of it. We've got your humerus and your ulna there, and we've got your bicep there connecting your humerus to your ulna. And for some reason, we've got a 5-kilogram bowling ball resting on the end of your ulna, your forearm right there. X-ray view, whatever. We need to find the force of the bicep on the ulna, assuming that the force is straight up like that. Force of the bicep, like that. So what kind of problem is this? This is a net torque is equal to 0 problem. This is another equilibrium problem. What are the things that are causing a torque on... Wait, what should we even be looking at? Well, all these forces are acting on the ulna, this forearm bone. So I think that we need to be looking at the net torque on the ulna. Should we be looking around a particular point? Yeah, probably. We should be looking around the elbow, because the elbow is where it's going to pivot around, or where it should pivot around, but it's actually not going to be pivoting around, as we talked about in the last problem, because we don't want it to pivot at all. So we can look around that point. It's often just easier to find the point around which something should be maybe pivoting, where it could pivot, and find the torque around that point. It's just simpler that way. So let's measure everything from that point. Now the elbow here is going to have some force on it. Do we know what it is? No. Do we care what it is? Also no, because the elbow is where we're measuring everything from. If we're measuring everything from there, then the radius from there is 0, and so it's just going to go away in our net torque equation. That's really why we want to pick a place like that to measure everything from, because we get to get rid of something that we don't even want to have to deal with. So let's do that. Let's measure everything from there. Well, we've got the force of the bicep. Okay, which direction is the force of the bicep? Sorry, obviously the direction of the force of the bicep is straight up. What is the torque? What is the direction of the torque of the bicep? Well, the bicep would want the forearm to go like this, to get lifted up like that. And that is like this, like that. Pushing something up like that. So that's like that, which is an out of the page torque. So that's going to be our positive torque. Our torque from the bicep is going to be positive. Okay, what is the other torque? Well, it's going to be the force of gravity from the bowling ball going down. Force of gravity from the bowling ball going down. Notice that I didn't call this the force of the bowling ball because that might end up making it slightly confusing. Whatever. We've got, oh, is this positive or negative? Well, it doesn't matter that it's going up or down, physically here or there. It matters that it's going in this direction. And that is an into the page kind of force, or kind of torque, excuse me. So into the page we're going to define as negative. Torque from gravity of the bowling ball is equal to 0. So the torque of the bicep is equal to the torque from gravity. The torque from the bicep, R cross F, bicep is equal to R gravity cross force gravity. Again, we've got a bunch of right angles. We've got everything measured from there. That's a right angle, that's a right angle. Okay, we're done. So radius bicep times the force bicep is equal to radius where gravity applies times the force of gravity. This thing is the thing we're looking for, the force of the bicep on the ulna. The radius from the elbow to where the bicep connects to the ulna is 0.05 meters times the force of the bicep is equal to radius where gravity applies, 0.35 meters, times the force of gravity. Force of gravity is, what is it? It's mg, so that's times the mass of the bowling ball, 5 times g, 9.8, and we can solve pretty quickly. We take 0.35 times 5 times 9.8 divided by 0.05, and we get 343 newtons. The force of the bicep is 343 newtons. You will notice that in all of the examples today, the angle was always 90 degrees. Obviously, that's not always going to be true. Next time, we're going to do some examples where the angle is not just 90 degrees. That should be interesting.